final example of this chapter, example 14. I had to split this video in two due to a dog-related technical issue. There you go. But anyway, this time we've got a pulley that's attached to the end of a horizontal plane. A of mass 0.4 kilograms. It's connected via a pulley on the edge of a horizontal plane to a block B of mass 0.8 kilograms. They're connected by light and extensible strings, the tensions are going to point towards one another. You need to check now carefully whether or not it's a smooth or rough horizontal plane. If it's smooth, there will be no friction. If it's rough, there will be friction that opposes it, because as this is released, this is going to accelerate down. This is going to accelerate to the right, and those accelerations must be the same because the string isn't extensible. And because the pulley is smooth, these tensions will be equal and opposite. It says that as there is a frictional force of magnitude 0.08 G, so this plane must be rough. So other missing forces were obviously the weights, 0.4 G and 0.8 G, and you've got the reactionary force of the ground onto block A, which must also be equal to 0.4 G. We first need to work out the acceleration system. The total time for B to reach the ground. Well, we're told that B was 0.5 metres above the ground when it was released. And we're also told that block A was 4.5 metres away from the pulley. So we've got quite scale issues in the diagram, but you know, there you go, we'll live with it. So in this system, it's going to be some rest. B is going to hit the ground. A will have moved across 0.5 metres, so it will be 4 metres away from the pulley when B hits the ground. When B hits the ground, the string will become slack. So at the moment it's tight. When B hits the ground, it becomes slack, tensions disappear. So we're going to have to split the problem up in two. As B accelerates towards the ground, and then after B hits the ground, when A will be moving across, but there'll be no tension. Alright, so let's work out the acceleration first. So we're going to have two equations of motion again. A system's motion, we're going to have one for A, one for B, one for A. Let's do A first. So A is to the right. So the resultant force to the right is the forces to the right minus forces to the left equals MA. So I've got T minus 0.08 G equals 0.4A. And for B, this time we're going to have the resultant force coming downwards, and that's going to be all the forces down minus all the forces up equals MA. So down is 0.8 G, up is T equals 0.8I. In order to work out tension and acceleration, I simply add them together. T's cancel, you end up with 0.72 G equals 1.2I. And if you divide by 1.2, it's what, 0.6, is it? 0.72 divided by 1.2, 0.6. So I is 0.6 G, which is 5.88 metres per second. So it accelerates quite quickly towards the ground. The question doesn't ask me to work out the tension, but I could easily find it now by substituting that value into this equation here, but I don't need to. Work out the time taken for B to reach the ground. So this is a Suvat question. Released from rest, acceleration is 5.88. It travels a distance of 0.5 metres until it hits the ground. Now I want time, so I need a formula that hooks up S, U, I and T. So it's S equals ut plus half that squared again. So 0.5 equals ut, which is going to be 0. So half I is 2.92. 2.94, sorry. Times t squared. So if we do a half, divide by 2.94, that's t squared. So square rooted. Obviously only after the positive answer because it's time. 0.412. Right, I'm going to look at the total distance from y before it comes to rest. In order to work that out, I'm going to need to work out the speed for which B hits the ground, because that will be the speed which A was travelling when the string became slack. Okay, so I can use V equals U plus AT. So V equals 0. So 5.88 times T. So I'm going to use ants in the calculator. So I need to just times that by 5.88. 2.42487. I'm going to put a few decimal places there because I don't want to get a rounded error later. Okay, so when B hits the ground, A has travelled 0.5 metres. So now I'm going to work out how far it travels after the string becomes slack. So after the string becomes slack, there is no longer any force pulling it forwards. You've got a force pulling it back of 0.08 g, which means it's going to accelerate in this direction. So it's going to slow down. It's going to decelerate. But let's do it in the direction of motion, because it is still travelling towards the pulley. And using RF equals MA, from left to right, the direction of motion. So we've got minus 0.08 g equals 0.4a. So minus 0.08 times 9.8 divided by 0.4 is minus 1.96. Now it's what you'd expect, because there's no longer any force pushing it forwards towards the pulley. It's going to slow down. It's slowing down at a rate of 1.96 meters per second every second. So we know, so now we can do suva. So this suva is from the moment the string becomes slack. So it's moved half a meter across. The speed at which B hits the ground was 2.4287. That's the speed A was travelling at when B hit the ground. So that's its initial speed, 2.42487. Its final speed it comes to rest is 0. And we know it's slowing down at a rate of 1.96 meters per second. We want the total distance travelled by before it comes to rest. So we want S. So we need a formula that hooks up S, U, V and I. And that's V squared equals U squared plus 2AS. So V squared is 0. U squared is 2.42487 squared. Minus 3.92s. So we're going to get 5.87999 equals, because that's going to move over to the side as positive, 3.92s. S equals, just divide that by 3.92, 1.5. Now be careful that that's not the final answer. That's how far it travels after B has hit the ground. So once B hits the ground, it slows down, and eventually comes to rest 1.5 metres later, but it had already travelled a half a metre, so the total distance is 2 metres. Okay, that is all the examples done in this chapter. So now have a go at exercise 10F, then have a go at the mixed exercise 2.